Alright, so welcome to a brief topic of organic chemistry. Organic chemistry would be the branch of chemistry that studies all of the molecules related to life. Many of these things include, the food we eat. If you really get into, medicinal organic chemistry, you're going to, do things with amino acids, DNA, medicines, things like that. One thing that just about all of these molecules have in common is they have carbon in them. Carbon is the atom of life. Okay, so amino acid has a central carbon. DNA, every vertice on this DNA structure, and the sugars and things like that, those are all carbons. Same thing in glucose, which is a primary fuel source for our bodies. Each of these corners represents a carbon. Okay, so carbon is the primary atom of organic chemistry. So we're going to start by talking about hydrocarbons. As far as organic molecules go, these are generally the simplest. All they have are carbon and hydrogen, hence the name hydrocarbons. Okay, now to save some time, there is a simpler way to depict hydrocarbons. The Lewis structures we've been drawing so far, you would draw out each carbon with the associated hydrogens attached to it. If you're writing a structural formula, you would write out the carbons and the hydrogens, but something that we will make use of to save us some time is this skeletal formula, or a skeletal picture. What each end of a line and each vertice represents is a carbon plus its associated hydrogens. Okay, so the skeletal formula, we're able to just draw lines instead of having to take the time to draw out each C and attach all of the hydrogens. We can just draw the skeletal formula as long as you recognize that each end of the line, each vertex, is a carbon and then the hydrogens it should have attached to it. So like on here, the end carbon should have 3 hydrogens, because it has another bond going towards the next carbon to fulfill carbon's 4 bonding requirement. Okay, this middle one is a carbon with 2 hydrogens, because it's connected to one C and then the last C out here, and then this last one has, again, 3 hydrogens. Okay, but you can leave off the carbons and their associated hydrogens and just draw the skeleton. Any other atom, when we get into functional groups and things like that, so if there's an oxygen attached, if there's a nitrogen attached, if there's a halide attached, those you have to draw. The only thing that you're allowed to leave off in the skeleton are the carbons and their associated hydrogens. Okay? So some more examples of that. This one would be we've got the CH3 group on the outside. Okay, so there's one carbon. Another carbon would be at the beginning of the double bond. So it's going to have one C. It's connected to the first C. It's also going to be connected to the other side of the double bond C. Okay, but it's going to have one more hydrogen to fill its 4. Same thing with the one on the other side, and then we'll have CH3 at the end. Okay. This really saves you some time when you get into long chains of carbons. Okay, so each end or vertex represents a carbon. Okay, outer carbons, as long as they're single bonded, will always be CH3s, and the ones in the middle will always be CH2s as long as they're single bonded. Okay, so outer is going to be a CH3, inner is CH2, and this is assuming single bonds, because as you double up your bonds, you lose a hydrogen. Okay? So, for example, what would the formula be for this last one? Right, we have one outer carbon, one inner carbon that's part of a triple bond, another inner carbon that's part of a triple bond, and an outer carbon. Okay? So the first one should be easy. You can tell it's going to be a CH3 because that's an outer single bonded carbon. Next one is going to be a single bonded inner carbon, so a CH2. at the triple bond, okay, there's 3 bonds between those 2 carbons, plus 1 bond to the next carbons on the outside, so do we need any hydrogens? No. So there's going to be 2 C's there, just on their own, and then a CH3. So, the biggest thing with organic chemistry is naming. Because if I give you a formula like C6H14, there's going to be several ways to draw that formula. Okay, the basic one would be to just draw it in a zigzag straight line, but there can be branches, there can be, maybe there's double bonds in there and then other things going on. So naming hydrocarbons so that it explicitly shows the shape of the molecule is vital to organic chemistry. Okay, we are going to start out with straight chains, okay, meaning there will not be any branches. So, for now, we will leave off the rules for branching. In that packet that I gave you, it does get into branching right away, but there's always at least one example of a straight chain one. So we're going to start there, get you familiar with all the pieces, and then we will add the rules for branching. Okay? So, hydrocarbons with single bonds only get called alkanes. Okay? Alkanes will always have the ending ane. That's how we're going to know that you mean only single bonds. Alright? The beginning of a straight line alkane, and these beginnings are going to stay the same for every possible organic molecule, is a prefix that tells you how many carbons are in your straight chain. Okay? So, most of these prefixes are similar to us. The first 4 are new in some ways. This is something you are going to have to memorize. Okay? Honestly, with this topic, especially as we get into functional groups and things like that, flashcards might not be a bad idea. But the prefix for 1 is meth, and then you add ane to make methane. Okay? So the prefix is the first part, the meth. There we go. Then for 2, the prefix is eth. And then for 3, prop. 4 is bute. 5 is pent. Okay, so up until the ane, because the ane is indicating that we're talking about single bonds. The 6 is hex. 7 is hept. 8 is oct. 9 is non. And 10 is dec. Okay, so especially starting at 5, those are your normal polygon number prefixes. Okay, so the ones that really should only be new to you are going to be meth for 1, eth for 2, prop for 3, bute for 4. So when it comes to drawing these are going to be the simplest ones. Okay, for butane, okay, you have your starting carbon, second carbon, third carbon, fourth carbon. Okay, so there's 1, 2, 3, 4. So we use the zigzag because at a carbon that has 4 bonds, what is the shape? Okay, the shape is going to be tetrahedral. Alright, so to account for the fact that this really doesn't form a straight line, it does actually form a zigzag line, take a model kit and actually make butane or propane, and you'll actually see that it makes, if you trace along the carbons, it actually does form a zigzag. Okay, and that comes into the fact that each carbon has a tetrahedral shape, so they don't form straight lines. Okay, so the next type of hydrocarbon is going to be double bonded one. Alright, so to indicate that there is a double bond somewhere in the compound, we change the ending from ane to ene. Okay, Now, what's different here is you generally don't run into carbons that are double bonded the whole way down. Okay? Generally speaking, you're going to have a chain that is mostly single bonds and has maybe a double bond, maybe a couple of double bonds scattered throughout. So the naming for this is a little bit different. You have to indicate where the double bond occurs. Okay? So for something like this butene here, if it falls on the first carbon, the double bond, then you call it 1-butene. Okay, because there's 1, 2, 3, 4 carbons, and the double bond occurs at the first carbon. Okay, whereas if you have a butene where the double bond's in the middle, you call it 2-butene to indicate where the double bond takes place. All right. So, ene, E-N-E, tells you that there's a double bond somewhere. The number tells you where it falls. Okay? So, you try naming or drawing these double bonded structures. Okay? One thing just to note, that around a double bond, you end up with a bent shape. So that kind of breaks up the zigzag. Okay? It forms a straight line through it. So that's why you don't draw a double bond angled down. You take it from the one carbon that they're attached to is bent in shape. Okay? So this first thing I always do is I count up my carbons, because that's going to get me my prefix. So I've got 1, 2, 3, 4, 5, 6, 7. So that's going to be a hept. I see the double bond, so I'm going to add ene. Okay, and then it's on the 1, 2, 3rd carbon, so this is 3-heptene. Okay, going from the name, I have 4 nonene. So non tells me that there's going to be 9 carbons. Ene tells me there's going to be a double bond, and I know it's going to be at the 4th carbon. Okay, so I'm going to draw 1, 2, 3. So this is 1, 2, 3 carbons. There's my 4th carbon, double bond. That's 5, 6, 7, 8, 9. Okay, so double check. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons, and it's 1, 2, 3, 4. That's where my double bond falls. Okay. So last one, coming up with the name. Again, I'm going to start by counting up how many carbons I have. I've got 1, 2, 3, 4, 5. So this is going to be a pentene. Now, as far as saying where my double bonds fall, these are a little bit trickier. Okay? Right now, the way this is drawn, I would probably say that it's carbons 1, 2, 3, 4, 5. Okay? So I'd say it's the double bonds are at 2 and 4. However, you can draw this exact same molecule with its mirror image, and it doesn't change it at all. Okay? So when it comes down to nomenclature, when you have things that happen in more than one place, okay, or you could assign it one of 2 numbers, you always assign the smallest set of numbers. Okay, so sometimes, depending on how your structure is drawn, you won't necessarily start counting from the left. You'll start counting from start from the side that is closest to something you have to indicate by number. Okay, so since our double bond starts on the end of this molecule, I'm actually going to start counting from that carbon. So I've got 1, 2, 3, 4, 5. This is 1, 3 pentene. As far as nomenclature goes, you separate numbers by commas. and in case you haven't picked up on it, there's always a dash between the number and the word. Just some nomenclature notes to keep track of. These are things that I expect you to do. Couple of questions to think about. Alright, so think about why I didn't show an example of methane. Okay? Or, especially now that we've talked about numbering, why don't I have a number for ethene or pentene? Okay? So, pause it, take a second to actually think about an answer to these. But, methane has how many carbons? You should be saying, based on that prefix, 1. To have a double bond, how many carbons do you need? You need a minimum of 2. Okay? So there is no methane because methane can only form bonds with hydrogens. Okay? You need to have 2 carbons to make a carbon double bond. Okay? Now, as far as ethene and pentene, think about the structures. Ethene, okay, essentially looks like this, with 1C, 1C, and your H is coming off of it. Can I ever draw that with the carbon double bond in a different position that would require a number? There's only one option for where the double bond can fall, so I don't need to include a number there. Pentene, on the other hand, you've got your CC, and then you're going to have another C. Okay? If I drew it this way, okay, you could sit there and say 1 pentene and 2 pentene, but those mean the exact same thing. These are just mirror images of each other. So again, you don't need numbering. The first time you need numbering when it comes down to double bonds is with butene. Okay, because there's no 2 different places for the carbon double bond to fall until you get to having 4 carbons. Okay, and then from there on, you have to indicate number. So triple bonded hydrocarbons, when you run into these, they are always going to form a linear shape around the carbon. Okay, so through a triple bond, including the carbons attached on the outside, there's going to be a linear shape. But to be able to tell these apart from a straight chain of all single bonds or a straight chain that has some double bonds in it, we change our ending to YNE or "-ine". Okay? And then formatting, as far as writing the names, is very similar to double bonds. You're going to start with a number with where it falls, dash to the prefix of the number of carbons, and the ending "-ine". Okay? Again, there won't be a methine because you only have 1 carbon and you need 2 carbons to make a triple bond. Okay, but ethine, you don't need a number because there's only 1 positioning for the triple bond. Okay, propine, same thing. There's only 1 positioning for the triple bond. But as you get bigger, say into pentyne, right, you do need to indicate numbers, and I'm noticing that I actually have a mistake here, and I want to see if you guys can spot it. So think about it. Look at the structure carefully. Is my numbering correct? So I made the cardinal mistake as far as numbering goes by taking my structure the way it looks and numbering it that way. But is there a way that I could have maybe reversed my drawing and had this come out with smaller numbers? Okay, so if you think about it being the reverse, C, triple bond, C, single bond, triple bond, C, CH3, that should be a CH. Okay, if I drew it that way, really the correct numbering here shouldn't be 2, 4. I can reduce it to 1, 3. Okay, so use this as a way to learn from my mistake so that you don't make those mistakes. Always think about it. Count from both sides of the molecule, go with the least numbers. Okay? So, here's some practice. Try drawing or naming the molecule. One thing before you do this, 1, 2, 3, fourth one, look at those two shapes. Make a decision as far as which one you think is actually the correct based on the molecular geometry of our carbons. So pause the video, get answers down for yourself, see how you do against what I give you. Okay? So first one, 3-octene. So oct means 8, ene means double bond, 3 is telling me where. So I'm going to have 1, 2, 3, double bond. That makes 4, 5, 6, 7, 8. Double check. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. There we go. Next one, need to count my bonds. Got 1, 2, 3, 4, 5, 6, 7. So that's going to be hept. I have no double or triple bonds, so it's heptane. Okay. Next one, 2-hexyne. So hex tells me there's going to be 6 carbons. The ine tells me I'm going to have a triple bond at the second carbon. Okay, so draw that one. This is going to give you the answer away for the next part. Around the triple bond, which is going to be the second carbon, there needs to be a linear shape, so there won't be any bending. So here's carbon 1, here's carbon 2, 3, 4, 5, 6. Okay, so my carbons are 1, 2, 3, 4, 5, 6. I have the hex, the triple bond is in there, and I have the triple bond at the second carbon with the appropriate shape. Okay, so this one, I've got the correct shape being here. Right, there will not be bending around a triple bond. And then to name this, I know I have 1, 2, 3, 4, 5, 6, 7 carbons, so that's going to be hept again. I have a triple bond in there, so it's going to be heptyne. And as far as numbering goes, I can count from, if I count from the first side, I have 1, 2, 3, 4, 5 where the triple bond falls. If I count from the other side, it's 1, 2. Go with the smaller number, 2 heptyne. And then I have 1, 4 butene. Okay, which means I'm going to have double bonds at the first and the last carbon. So the way this one's written, I think it'll still make sense where the double bonds fall. So I have 1, 2, 3, 4. So here's my carbons, 2, 3, 4. Butene can only have 4 carbons, but what's wrong with the name? Okay. You always name the starting carbon where the bond begins. So this really should be 1, 3 butene. It could have been 1, 4 if, say, it was a pentene, and you had a 5th carbon in there. Okay, but correct naming based on the number of carbons present should have been 1, 3 butene. Okay, so use some of the mistakes in here. I'm hoping that they might actually help as far as preventing you from making them later. Okay.